Hello, I am Feng. And the topic of the paper I'm going to talk about is algorithm design and simulation of rectilinear Steiner tree problems based on concrete class line. I will explain the following four aspects. The first part is overview. The second part is algorithm design. The third part is analysis of simulation results. And the last part is summary and outlook. The first part, overview. The Steiner tree problem infancy. The Steiner tree problem belongs to the discipline of the conventional optimization. It was first developed in the 19th century by the Swiss scientist Steiner, who generalized it to find a point on the plan such that the sum of the distance from this point to a given number of points on the plan is minimized, which is the prototype of Steiner's problem. The Steiner tree problem development over the centuries, a number of minimizations have extended the problem, making the Steiner tree problem even more profound and amending the term introducing a point to introducing a number of points. Based on division in the plan, a Euclidean Steiner tree is a Steiner tree in the Euclidean plan which requires that the two edges past a point have an obtuse angle of 120 degrees, and that all Steiner points must be within the convex envelope. If the region enclosed by the connection of n-terminal vertices is a convenient envelope, the distance of the connection between 2 points and a x1, y1 and b x2, y2 is calculated using the Euclidean distance d. The equation below is for calculating the Euclidean distance. For a linear Steiner tree (RST), it is required that the two sides past a point must be 90 degrees, and that all the connecting linear are perpendicular to each other. Hence the name right-angle Steiner tree and perpendicular stick distance Steiner tree. The distance d1 of the line between 2 points a1, x1, y1 and b1, x2, y2 is calculated using the absolute value distance. This paper investing a sub-case of the rectilinear Steiner tree (RST), the MRST. As the name suggests, a minimum rectilinear Steiner tree is a Steiner tree that finds the shortest total length of the connected line and the smallest total cost among many rectilinear Rectilinear Steiner trees. The earliest actual algorithms were based on iterative implementations, either based on spanning tree enumeration or on topology emulation, and I have calculated the actual algorithm posed by some of the research in this table. Next, I will describe the research ideas and methods. For the Steiner tree problem, there are four classical algorithms in terms of hierarchies, which are briefly described here. The first one, simulation annealing algorithm, refers to the problem of the similar and combinational opposition of the annealing process of styling measured substances. The second is a component algorithm, is the ability of art to release a phenomenon on a path when searching for food. The second is that generative algorithms are the most basic type of operating algorithm. The first is that particle swarm optimization algorithms are derived from genetic algorithms. Particle swarm optical algorithms are derived from genetic algorithms. The parameterization algorithm is also an important algorithm because of the large number of terminal vectors and the complexity of the graph when used in parties. The parameterization algorithm was developed. The parameterization algorithm is a parameterization of the Steiner tree problem. The classical parametric algorithm is the DW algorithm implemented based on dynamic programming techniques. The dynamic programming techniques is also one of the most widely used techniques to solve the Steiner tree problem, and is the core idea and technique of the algorithm in this thesis. I will then introduce the second part, algorithm design. The principle of the algorithm is based on the implementation of dynamic programming techniques using the idea of decomposition, where for each subset, all decomposition cases are considerable to find the optimal linear Steiner tree. With regard to dynamic programming, the problem to be solved is decomposed to a number of sub-problems, which are first solved and then the solution of the original problem is ambitioned from the solution of these sub-problems. The sub-problems are not nominally independent of each other. Two algorithms has been designed in this paper. Two algorithms are used in this thesis: LMRST and ZMRST, both of which are based on the base class line and designed using the same solution pattern in the structure design pattern, but differ only in the specific iterations. The following diagram shows the procedure code for one of the key algorithms. Next, I describe some of the key points of the algorithm. The RST class is a common simulation mode for solving a linear Steiner trees. The second point is the MST class is used to solve the linear minimum spanning tree. In preparation for the subsequent algorithm for solving all the A's in it after generating the minimum linear Steiner tree. The third point is the Visualize class. Connect the OpenCV Visual Library. First use a for loop to process all the generated A's. Store and color them black. Then use another for loop to process all the points, color them, and finally generated a tree to be displayed as a graph. I will then briefly describe the process of these two algorithms, starting with the LRST algorithm. LRST is to select L-shaped or U-shaped layout for each edge. Among all layouts, overloop is largest. First, build the tree. The find root function does this by selecting a node of degree 1 as the root. Then we recursively build the tree using the list of edges found in the MST function. The tree is represented by two arrays, tree and parent. Then there is the ZRST algorithm. For each edge, ZRST processing all feasible Z layouts. Since the Z layout can be uniquely identified by its inflection point, it is possible to represent a layout by saving the coordinate of this inflection point. After the tree has been built by the build tree function, it is called recursively for the root of the tree. For each node traveled, all its children are first traveled, and then all possible layouts are imitated for the current point. In the third section, I will talk about the analysis of simulation results. The following two figures show the results of the LRST and MRST algorithm for a num of 500. The total path length of LMRST is 8,480. And the total path length of ZMRST is 8,432, which is not a big difference. I have summarized all the expectation data in the table below, and it is clear that for both algorithms, there is no difference in the total length of the linear Steiner spanning tree when the number of terminal vectors is small, less than 50. And at larger number of terminal vectors, the total length of the linear Steiner spanning tree of ZMRST is shorter, and the results are better than those of the LMRST algorithms. Finally, in the first part, the summary and outlook. In this paper, two algorithms for MRST problem are presented based on dynamic programming technique. It can be seen from the analysis that ZMRST has a slightly better calculation results because ZMRST pre-compiles are possibly aids, but while obtaining better solution, the time cost kept increasing. With regard to the outlook in this direction, linear Steiner tree has important applications in VLSI problems, but for implementing VLSI warning problems, how to guarantee quality, even if the final guarantee line is shortest and the wearing time is shortened, and the algorithm is stable. There is still a lot of room for improvement in this algorithm. This concludes my talk. Thank you.